To finish up, just a few more important effects, but these are all at much, much smaller magnitudes and really apply when you're operating away from near planetary orbits. So these are mostly for natural bodies in the solar system and for spacecraft in interplanetary space. We have radiation pressure, Poynting-Robertson drag, and the Yarkovsky-O'Keefe-Rejevsky-Paddock, or YORP effect. Radiation pressure is the acceleration generated by the interaction between mass and electromagnetic fields. Remember, photons, while massless, still have momentum, and they can impart momentum on masses. And this can either be a perturbing effect, or if you build a device like a solar sail, can be used as a method of propulsion. Although again, the acceleration magnitudes are very, very small because photons are, while they have momentum, are tiny, tiny quantas of momentum. We can define something called the Poynting vector. S is the Poynting vector, and it is defined as the electric field vector crossed with the magnetic field vector, and this makes this equivalent to the energy flux. The average energy flux over the speed of light is called P. So the radiation pressure P is this Poynting vector averaged divided by the speed of light, which is the speed at which photons travel. Recall from Einstein, everybody's favorite equation, E is equal to mc squared, which means that mc is equal to E over c. mc is the momentum of a photon, and that means that P is equivalently E over c. The force due to radiation pressure, we can write negative this pressure value times the reflectivity of our object, which we call C sub r, times the area exposed to light, and then assuming that the light is due to the sun, this is all in the direction of the position vector of our mass with respect to the sun. So the force is always acting away from the light source. And as previously stated, this is the inherent principle behind a solar sail. The idea of Poynting-Robertson drag is that solar radiation causes dust grains to spiral into the sun. Light moves much, much faster than the dust. This dust is not moving very quickly, and the actual rate at which it spirals in is dependent on the size of the dust grains. The other important thing to understand is that photons are going to be absorbed in the radial direction, but re-emitted anisotropically. And that leads to an overall loss of angular momentum for various elements of your dust cloud. And putting these two things together, what you'll find is that the solar radiation is actually causing dust grains to spiral into the sun. The Yarkovsky effect is the idea that rotating bodies release thermal photons anisotropically. You will have a rotating body, say an asteroid, and this is especially pronounced for small things, meteoroids and small asteroids. Will have a measurable effect on the object's momentum because they are shedding thermal photons randomly in different directions. Over long enough timescales, this will actually change the orbit. And this leads to a really cool idea for asteroid deflection. For planetary protection, if we ever need to move an asteroid because it could potentially impact the Earth sometime in the future, all we would need to do, assuming we had sufficient time, would be to paint one side of the asteroid bright white, and then just wait. And this would, over many orbital periods around the sun, cause a perceptible effect on the asteroid's orbit. So Yarkovsky is the anisotropic emission of thermal photons, leading to changes in momentum. The Rejevsky effect is that a change in the albedo, which is the reflectivity or the brightness of an object, will change its rotation rate. And then the O'Keefe-Paddock effects are that the object shape will affect the spin rate. So you put all these together and you get this idea of YORP. All of these things make it incredibly difficult to pin down the exact orbit for small asteroids, because any current orbital fit is going to be constantly modified by the persistent action of all of these small effects over long periods of time. And so this is why, just like tracking a spacecraft in Earth's orbit is very difficult long-term, tracking the orbits and predicting out the orbits of small natural bodies in the solar system long term is also inherently incredibly hard because it requires precise measurements of lots of effects that are somewhat stochastic and incredibly hard to pin down.